Greetings, my name is Luis Javier Ontañón, and on behalf of my coworkers, this is a brief introduction on the article Electronic Implementation of a Dynamical Network with Nearly Identical Hybrid Nodes via Unstable Dissipative Systems. The premise of the article is that almost all the networks in the physical real world are composed of nodes that are non-identical, or at least nearly identical among them. One of the most common examples of this is in electronics, where every component manufactured presents characteristic tolerances among them. In this article, this problem will be attended and a solution will be presented both by numerical and experimental results. In order to obtain nearly identical nodes on the network, we will be focusing on the unstable dissipative systems of the type 1 theory, which was first introduced in the reference number 8. In this case, the idea is to have a piecewise linear dynamical systems in a three-dimensional space that presents an hybrid part given by this capital B. The values of the coefficient matrix will be given as depicted here in equation 2, and the affine vector will change regarding the position of the x sub index 1 state as follows. The idea is that for each domain on the space, in this particular case, two values will be given. One when x1 is greater or equal to 0, and minus 1 when x sub index 1 is less than 0. After solving the system with a numerical integration method, the time series will result as given in figures 1, A, B, and C. Figure 1D represents the projection onto the plane x1 and x2. Notice the two scroll attractor in which the system results. This particular type of UDS system presents chaotic trajectories, although their mathematical expression is very simple. And since chaotic systems can result in completely different trajectories for fairly identical parameters, they result as an excellent choice in designing nearly identical nodes. In this case, we will consider these systems as part of a nearly identical network. The second part of the presentation will describe the structure of the network. The network is given by equation number 10. Here it can be seen the UDS system represented by this term, and the second part will be composed as the network expression, from which we can see that the variable C corresponds to the coupling strength among the bidirectional connections among nodes. The term delta stands for the network topology, which its diffusive coupling matrices according to different structures will be given in the article in equations 11 and 12. The variable gamma corresponds to the inner coupling matrix, and at last the parameter alpha sub index I represents a tolerance value that will make each node nearly identical. Generally, in electronics, the tolerances are values between 5 to 10%. Here, in this case, In order to study further possibilities, the tolerance at each node will be given randomly between plus minus 20%. Two network structures will be studied. First, a nearest neighbor connection, and second, a fully connected network, as depicted by the graphs of figure 2a and b. In case of the study with the numerical simulation, 10 nodes will be considered in order to reflect if the network is synchronized or not. Since the nodes are nearly identical, it will not be suitable to study identical synchronization among the network. Therefore, practical synchronization will be considered. In order to determine if two nodes are practically synchronized, the Euclidean distance among the nodes will be calculated. First, a study on the variation of different coupling strengths will be considered from a range between 0 to 2.5. Each value of the graph A in figure 3 corresponds to a single experiment for different coupling strengths. Notice that in the case of a fully connected network, the Euclidean error falls abruptly to 0 by taking all the error values in the simulation. Now, an average of all these values here in the simulation will be taken in an average in order to determine the value of epsilon sub index max. This value will determine if the nodes in the network are practically synchronized when the error between them falls beneath this value. Similar considerations are given for the nearest neighbor connection. Notice only that the Euclidean distance falls for greater values. In this case, for a fully connected network, we have 0.01 approximately, and for a nearest neighbor, we have 0.08. The time series of the 10-node networks are depicted in figures 4 and 5. First, in figure 4, for a fully connected network, the experiment conducted was to leave the node autonomously before the time 100. In this part, we can see that each node initialized with different conditions, each nearly identical node oscillates autonomously. After the arbitrary time of 100, the coupling strength is set to 0.5, and after that time, all the nodes in the network are practically synchronized. This is the time series for x sub index 1, for x sub index 2, and x sub index 3. Figure D shows now the Euclidean distance, but a long time. The only coupling strength given here is 0.5. Notice that after the value of 100 in which the network is coupled, the error falls below epsilon sub index max, which is, as previously said, 0.01 approximately. Similar characteristics for the nearest neighbor configuration, although after the coupling strength is given also as 0.5, some differences can be appreciated from the figures. In this case from x subindex 1, subindex 2, and subindex 3. Notice that these small values are fairly seen here in the Euclidean distance, and now the error between these nodes is greater than before. But all these values fall between the parameter calculated as epsilon subindex max, which is 0.08 approximately. So both experiments, as the fully connected network and the nearest neighbor configuration, can be considered as practically synchronized. The last part of the presentation is given to the physical experimentation. In this case, considering the analog computational method, the equation of the network node were converted to analog electronics using operational amplifiers. The advantage of using the UDS hybrid systems is that the system presents chaotic behavior with no multiplication of the states or other complicated nonlinearities. Figures 6 to 8 describe one single node in the network. Since the value of the coefficients are set as gains in the op-amp configuration with basic resistor and capacitors, the electronic implementation presents intrinsically the tolerances values of alpha as described before. Here, in figure 6, it can be seen that the circuit diagram of the states x subindex 1 and x subindex 2 are represented in the article as the equations 13 to 15. Figure 7 represents the electronic implementation of the state x subindex 3 and figure 8 represents the commutation affine vector from capital B of the equation 1 as given as the circuit diagram of figure 8. In this case, a comparator was implemented in order to make the values commutate to the value B subindex 3. Finally, the connection between nodes are represented in figure 9. Each subcircuit marked as magenta, green, and cyan correspond to the coupling strength and connection among the states of x1, x2, and x3. Seeing first this x1 connection, it can be stated here that each one of the nodes corresponding here is a connection among one particular node. In this case, this is the first node, the second node, a third node, and a fourth node. The gain of this amplifier is given as F1 and represented in equation 16 of the article. This entire connection corresponds to the connection amongst nodes in the x1 state, the x2 states, and the x3 states, respectively. Since the circuit diagram of each particular node is composed as a high number of components, only 4 nodes will be considered in the physical experimentation. In this case, 4 nodes connected in 2 different configurations will be considered. First, a nearest neighbor connection, represented here, and second, a fully connected network, considering that each one of these nodes will be given the circuit diagrams from figures 6, 7, and 8, connected as depicted in figure 9. The experimental traces from the oscilloscope of the systems are given here in figure 11. It can be seen that for the nearest neighbor connection, the following results were obtained. In this case, we have the signal of the state x1 for the first node. Here we have the signal of the same x1 state, but for the node 2. Here for the node 3, and at last for the node 4. All these traces correspond to the states of the x1 state. Between them, here in a small blue pale line, is the Euclidean error between the state 1 of the node 1 and the state 1 of the node 2. The second line corresponds to the error between the state 1 of the node 1 and the state 1 of the node 3. And finally, this line corresponds to the error between the state 1 of the node 1 and the state 1 of the node 4. Notice that the values of the oscilloscope are given below 100 millivolts, and this Euclidean error is very small according to as planned before, with the epsilon subindex max value, resulting in a practically synchronized network. In this case, the coupling strength given to the network was 2.5, assuring that the system will be practically synchronized. Finally, for a fully connected network, the same characteristic. Here we have this x state 1 for the node 1, x state 1 for the node 2, state 1 for the node 3, and state 1 for the node 4. Also, between each one of these lines is the Euclidean error between the node 1 and each one of the particular nodes. Notice that the error is smaller in this case. Also, the values are below 100 millivolts. Both networks oscillate similarly as the chaotic system response, and both networks are practically synchronized. In this case, since the connection of the systems are since the connections are graded in this system, we are using a coupling strength of 2. So both systems were practically synchronized. To conclude with this explanation of the article, let's summarize what was seen. First, we talk about the nearly identical chaotic nodes and how does the chaotical properties falls well in order to design different systems. Second, the network structure was defined and the numerical simulation was implemented in order to prove the practical synchronization among the nodes. And third, physical electronic implementation of this network, in which different types of connections can be implemented due to the easy dynamics of the operational amplifiers, was presented. The concluding remarks of the article are summarized as follows. First, the hybrid piecewise linear in the UDS configuration was suitable in the design of nearly identical networks due to the chaotic properties. Also, the simple structure of the mathematical expression was convenient in the design of the electronic circuit implementation of the network. Second, the proposed network considered a tolerance variation in the parameters of each individual nodes, resulting in non-identical systems similar as real-world network structures. The tolerance given into the network was forced to be relatively higher than in physical systems in order to study practical synchronization. And finally, this practical synchronization behavior was obtained both in the numerical simulation as well in the physical electronic implementation. This guarantees that nearly identical nodes can be coupled and that the electronic implementation results as an important tool to study different connections among nodes. The authors of this article would like to acknowledge the investigation group Optimización y Ciencias de Datos for the support given, and also acknowledge the financial support given by the Fondo de Apoyo a la Investigación and the Secretaría de Educación Pública.